Let's stick with that same buffer. Why not? Let's stick with we have, but let's change the volume. Let's say we have 2 liters this time of a 0.100 molar acetic acid and 0.100 molar sodium acetate buffer. And we're going to draw a picture here. Do a big flask. And we got 2 liters of this stuff this time. We are going to add 50.0 milliliters of 1.50 molar hydrochloric acid. And I want to know what's the new pH. Okay, so we got a buffer. This time we got 2 liters of this buffer. It's 0.1 molar in acetic acid, 0.1 molar in sodium acetate. We're going to add 50 mils of 1.5 molar HCl solution, and I want to know what's the pH after I've done that. And we got a couple problems here. Okay, number one, we're adding 50 mils of this. The volume is going to change. We're going to go from 2 liters, right, up to 2.05 liters because we're adding, the volume is changing. Okay, we also, I don't directly give you the moles of acid that's being added. We're going to have to figure that out. But the first thing we should do before we get too far ahead of ourselves is figure out which part of the buffer is the HCl going to react with. Well, the HCl is going to react with the sodium acetate. Okay, so I need to write out that equation. So the equation is going to be HCl reacts with the basic part of the buffer, which is sodium acetate. Strong acid, so a single-headed arrow. Okay, that is going to create more acetic acid, and it's going to create sodium chloride, which is, neutral salt. Now, you could have gotten rid of the sodium and the chloride, really, if you wanted. They're both spectator ions, but it's fine. Next, after we make that, we're going to create our BAA table. That sodium chloride is a neutral salt, so we can get rid of that whole column. Now, BAA table, everything must be in moles. So we haven't added any HCl in the before the addition. No, this is before the addition. That's what we're adding, so we haven't added any of that yet. That's coming, but we haven't added it yet. I need to figure out how many moles of sodium acetate are in here and how many moles of acetic acid are in here. How are we going to do that? We have the concentrations and we have the volume. So that's where molarity is going to come into this, right? Molarity equals moles per volume. Multiply both sides by volume. The moles is equal to the molarity times the volume in liters. So to get the moles of the sodium acetate, we take the molarity, 0.100 molar, times 2.00 liters, and we're going to find that that's 0.200 moles. Remember, capital M molarity is an abbreviation for mole per liter, so liter cancels out. That's where the moles come from. Now we need to get the moles of the HC2H3O2. So the moles of the acetic acid, that's going to be 0.100 moles per 1 liter times the volume, 2.00 liters. And that's going to be 0.200 moles. Cool. Cool. Now, we need to get the moles of the addition. We're not adding any of those. So now how many moles of acid am I adding? I need to do the same thing up here. I need to take that concentration, 1.50 moles of HCl per 1 liter, and I need to multiply it by its volume in liters, divide that by 1,000, that's 0.0500 liters. So if we do 1.5 times 0.05, that's going to be 0.075 moles. So we are adding 0.075 3 sig figs, 0.0750 moles. Love it. So what's going to happen? Well, I have enough moles of base in here to absorb that acid. So there will be no acid left over. I'm going to subtract to see how much base is left over. So 0.2 minus 0.075, that's 0.125. I'm then going to add that to that because I'm going to, when these react, I make more of this. So I'm going to make that. So this is going to be 0.275 moles. So you can see we still have a buffer intact. We have the basic component of the buffer and the acidic component of the buffer. We still have a buffer here. Now, since we still have a buffer, that means we can Henderson-Hasselbalch this thing. So pH equals pKa plus the log of the basic component, that's the acetate, divided by the acidic component, that's the acetic acid. Now, how do I get these back into concentrations? Well, I now need to divide these by the new volume. Remember, molarity is moles per volume, but my volume has changed. I had 2 liters in here to begin with, and I dumped in an additional 50 milliliters, which is 0.0500 liters. So my new volume is now the sum of that. It's now a 2.05 liter solution. So I need to divide these by that new volume, 2.05 liters. So 0.125 divided by 2.05. My acetate concentration is 0.0610 molar, and my acid concentration is 0.134 molar. So now I'm ready to rock and roll. My pKa was 4.74. The basic component of the buffer is 0.0610 molar. The acidic component of the buffer, 0.134 molar. So 4.74 plus the log of 0.061 divided by 0.134. And we get a pH of 4.40. This buffer did a pretty darn good job. We just added 50 mils of a 1.5 molar strong acid, and the pH goes from 4.74 in the 1-to-1 buffer down to only 4.40. 4.40. It absorbed a strong acid, a decent amount of the strong acid, in fact, and the pH only dropped a little bit. Not even just a little more than 2/10 of a pH or 3/10 of a pH unit. So that's not too bad. So I want to do this problem right here. Okay, give me a second. I'll copy that down. Okay. So right away, what kind of buffer do we have? We have a weak base conjugate acid buffer. Okay, which means we are using the basic form of the Henderson-Hasselbalch. POH equals PKB plus the log of the concentration of the conjugate acid, in this case ammonium, divided by the concentration of the weak base ammonia. Okay, I did have a weak base. I thought we'd just wait till the lab, but we'll do one of these guys tonight. So how do we get the pOH of this? Well, the pOH equals the pKb, 4.75. Now, if this was a 1-to-1 buffer, if it was 0.2 to 0.2 or 0.5 and 0.5, if it was 1-to-1, then the pOH would just be the pKb. But we don't have a 1-to-1 buffer, so the pOH will not be the pKb. Okay, just like in the acidic form of the Henderson-Hasselbalch, the pH is the pKa if it's 1-to-1. And in the basic form, the pOH is the pKb if it's 1-to-1. So this is going to be plus the log of 0.20 divided by 0.50. So let's pop that in there. And we get 4.35. 4.35. But wait, I want the pH, and this is the pOH. So 14 minus that, the starting pH of our buffer is 9.65. If you stuck a pH probe in there, it would read 9.65. That's our prediction. And now I want to add something to this buffer. So I don't care, the last slide, it had two problems, but let's just make up our own. Let's add our own kind of thing to this buffer. So what are we going to add? Oh, man, we just added an acid. Let's add some base to this buffer. We are going to add 85.0 milliliters of 1.15 molar potassium hydroxide. And I would like to know, after we dump in the 85 mils of 1.15 molar KOH, what would our pH read then? Because it ain't going to read 9.65. We're adding a base, that pH is going to go up. But since it's a buffer, it shouldn't go up too far from 9.65. Hopefully, we're going to find out. First thing we need to do is say, what's this going to react with? Well, this base is going to react with the acidic component of the buffer. Let's get rid of the spectators. Chloride is a spectator ion. Potassium is a spectator ion. So let's show ammonium reacting with the hydroxide. What are we going to get? The hydroxide is going to rip a hydrogen off of here. We're going to get water. And then we're going to get ammonia, NH3. And then we need to make a BAA table. Cool. So I need to fill out my before addition row. So I haven't added any base yet. No hydroxide's been added. How much ammonium is in here before I added, and how much ammonia is in here before I added. So here we go. That's where the moles is equal to molarity times volume. So to get the ammonium, it's going to be 0.20 moles of ammonium per 1 liter times the 2 liters. And 0.2 times 2 is 0.4, right? So that's 0.400 moles of that. Now I need to do the same thing for the ammonia. So 0.50 moles per liter times the 2 liters. And that's going to be 1 mole of ammonia. So now I need to figure out how much hydroxide I'm adding. So once again, concentration 1.15 moles per 1 liter of potassium hydroxide times 0.0850 liters. That's going to be 0.0978 moles. So let's look at what we've got. I've got enough acidic part of the buffer to absorb that added hydroxide from the potassium hydroxide. So I'll have no hydroxide left. I'm going to subtract here. So 0.4 minus 0.0978. It's going to be 0.3022. We'll worry about sig figs at the end. I'm going to add that to here. So that's going to become 1.0978. Again, we'll do the sig figs at the end. And now I need to divide by my new volume. Well, I started with 2 liters, and I've added 85 mils. So that's going to be 2.00 liters plus 0.085 liters. It's going to be 2.09 liters. I'm going to round it to the hundredths place because of the addition, subtraction, sig figs. So now I need to divide these by the 2.09 liters. So 0.3022 divided by 2.09. That's going to come out to 0.145 molar in ammonium. And that's going to come out to 0.525 molar in ammonia. And now I can use the basic form of the Henderson-Hasselbalch equation. So POH equals the PKB, which is 4.75, plus the log of the acidic part on top, 0.145, divided by the basic part, 0.525. And the POH will equal 4.19. And we are almost done. But I want the pH. So to get the pH, it's 14 minus the 4.19. And we get 9.81 as our pH. Now, we said the solution was starting with a pH of 9.65. We just added a whole bunch of a strong base, and the pH only went up from 9.65 to 9.81. That's impressive. That's what buffers do. Buffers resist changes to the pH. If I added that much base to pure water, the pH would go, 12 or whatever, it would skyrocket, right? It'd be huge. So yeah, that's how we kind of work our way through those.